自然を取りに渡り行きます。
結構来てますよ。いいと思う。大丈夫じゃない？
Change the key number from being 3.14 to twice that because it makes our equations easier. Now, that's much more arguable because you're really doing a subjective question about whether or not an equation looks easier. In this case, we're actually dealing with something that you can't really argue with. C is such a fundamental part of what space-time is all about, the speed of light in space, or the speed of any self-propagating energy in space. I don't want to say light is the only form, right? There could be other forms. For example, if neutrinos didn't have mass, they would all travel at the speed of light. It turns out they didn't have mass, so that's not a point, but for a while when I started studying this, it was unclear. So this is so fundamental that it's screaming at us to make this the fundamental constant, to measure all of these things in the same units, and that's what we're going to do. Now, there's another unit issue that's probably worth talking about a little bit regarding energy, so let's look at that. But wait, before we look at that, how does all of this affect everything here? Well, we end up losing g and c to the fourth, and you keep this 8 pi. So what's that 8 pi all about? Right? And that has to do with the Newtonian limit, right? Coming back to the Newtonian limit. And the pi's and the 8s and the 4s and the 2s, they show up in the Newtonian limit because of the way the force law was written. Ultimately, we had this force law, and the force law was written in such a way there was something called gravitational potential in physics and Poisson's equation, and there's integrals over spherical volumes, and that's where the pi's start to show up. So it becomes, where do you want your pi's to show up? Do you want them to show up in the field equations? Do you want them to show up in Lagrangians? Somewhere. And the place where you put them is actually a distinction. This actually matters more in electromagnetic theory, where you have different types of unit systems. Actually, these pi's are being squeezed into different places. Not something we need to talk about here, but that's the origin of the 8 pi ultimately is the Newtonian limit of all this. That Newtonian limit has this problem of how to track various integrals around spherical surfaces, and you just decide where to put it. So that's where that comes from. So the rest of this, though, is just that this stuff here now, what's left, is what we're going to ultimately learn about. We're going to learn about Einstein's field equation, what it means and why it's important. The only thing in this that you should recognize already is this guy. G nu nu. And G nu nu comes from our what is a tensor prerequisites. And it is a tensor field. It is a 1-1 tensor. I'm sorry, it is a 0-2 tensor field. And therefore it is understood to be a function of space-time, where x is a coordinate inside our space-time. And then the part about the manifold is that's so important, is that coordinate in space is a property of a manifold. If you have a manifold, which is what we're going to use to model space-time, you know you can. It's because that's the definition of how a manifold is built. So this is a tensor, a 0-2 tensor field on a manifold. The manifold is modeling space-time. The 0-2 tensor field is the metric tensor, which establishes an inner product at every point in space-time for comparing vectors located in those tangent spaces. If what I just said doesn't make a lot of sense to you, then the prerequisites, you're a little bit behind on the prerequisites for where we're going to go. I'll be repeating these things again as we go, so I won't be like I'll just refer to them without any review. Ultimately, this thing here, the cosmological constant, it's probably not something we're going to talk about in the early part of the course because we're going to go right into the mathematical modeling of space-time and black holes and non-cosmological models. So probably not going to deal with that. We're going to set it equal to 0 basically. But this guy, he's a big part of the story. The Ricci tensor is a huge part of the story. Same with the curvature tensor. And then there's another tensor from which all of these guys are made, the Riemann curvature tensor. This guy here is ultimately this is the matter side of the equation, and this is the space side of the equation. This is the matter side of the equation. Right? And ultimately that represents the distribution of matter, where matter is very broadly understood to be mass, energy, light, fields, anything that we can consider nothing. Anything that's not a vacuum is essentially matter. Okay, but there's another unit issue we might want to come back to, and that's the special relativity style questions. So let's have a look at that. So in this tradition of taking fundamental things and turning them into unitless numbers, we have the problem of the charge of the electron. I'll write down as E, charge of electron. Now, putting aside the issue that E, the charge of the electron, is always treated as a negative number, and probably should have been positive. This is another one of those things that people always, in retrospect, people would go back and change, but nobody really has the stamina to make it happen. But the charge of the electron is evidently a fundamental number in physics, and it's arguably the real fundamental number is 1/3 of.
映画は好き。映画は太郎左衛門が植えたというイメージ。
The charge, come in with this kind of charge, because of issues of be separated from one another, it is very safe to say that we is a fundamental charge of the electron. But so E is measured in Coulomb. the meters in seconds maybe, but the charge of the electron goes to 1, so it ends up being electron volts in that circuit. Now, so what does this now imply? Well, energy is and we've also made the choice that C equals 1, right? Then the problem is that we now know that energy is also equal to mass, right, times C squared, right? Energy is mass equals MC squared, right? Energy is mass times C squared, but C squared is 1. So we end up with this idea that mass is also going to be measured in electron volts, right? Right now we're talking about special relativity, so G is out of it, right? We're not talking about G now. We've only said C equal to 1 and E equal to 1. So mass has to also be measured in electron volts. And that makes a lot of sense because we always have this equation, this idea, this E equals MC squared idea, which basically says energy can be directly proportional to mass, and the constant proportionality is C squared. But if we make C squared 1, then we get energy equals mass, right? Now, the other problem with this is we end up with momentum, P, right? And P equals mass times velocity. But velocity is now unitless, right? So the units of momentum have the mass, which is of energy. We're going to go with as electron volts. So all of these things end up with the same units as well. In the special relativity system, this is the special spec-rel world, right? And so our equations in special relativity, that's where when you use this, equations become much cleaner. You end up without all of these little C squares everywhere or C powers everywhere that you do see in the most elementary treatments of special relativity. C to the fourth. You may want to redo some of that, go to a different book that actually uses this system of units, which are called natural units, and start over and review it using this system of units. We won't have to do this much. I will talk a little bit about this in one of the earlier lectures, but ultimately this is the units. We use these geometrized units. Did I say that? Did I say that this was called geometrized units? Let me make sure I say that. This is geometrized units, and that's the units we're going to use. Okay, so what else do we have to talk about as a preliminary matter? Well, I guess we could talk about sort of the syllabus thing, right? And I want to confess that I don't exactly know the way to go through this. There are two choices, though. Roughly speaking, the way I see it, there's two choices. There's the Einstein equation, right? A pi t mu. We can start by discussing general relativity in general. Come up with some motivation for the Einstein equation, which is actually pretty hard. Remember, Einstein thought a lot about this thing. He went through a lot of struggle and turmoil and came up with it, and it worked, right? So there's no just automatic method to go from point A to B and derive the Einstein equation straight from some fundamental basic principles. Arguably, you can do it. You can go through the equivalence principles and other things like that. But it's very nonlinear, and it's almost philosophical. And you're really basically kind of saying, hey, I think the universe operates through tensor equations, and this is really the only logical tensor equation that works. And
綺麗だった。どっちこっちやるの？こっちやく。え？また帰ってくるから。誰かに言ったんだけど。こっちがないの。
syllables, I would kind of give some service to that. Or another. And all the books do it. All Michael Dorn it's about the equivalent principle. DeVano's got some really great chapters. I know his handling of it. We'll probably go through these and discuss them. But my insight into this is certainly not going to be anything different than these books. And this is a very good hypothesis equation of how the universe works, and it's very fruitful in the end. So look, we can talk about that, and then we use the Einstein equation. The goal of that whole thing, arguably, but the way I would do it in my course, is to learn how to calculate the structure, I'll put that in quotes, of space-time. And whenever you talk about the structure of space-time, you only need one thing, the metric. We use the Einstein equation to calculate the metric. And I'll put the little X there to show that it's a metric field, the metric field. And the way this is, the theory here is that I know the mass distribution, the energy distribution, or in the space, and from that I calculate this Einstein tensor, and from that I extract the metric. Right? So this is how matter, where I use matter in a very general way. Although when I say matter in a general way, what I mean is electromagnetic energy counts as matter, light counts as matter, anything that's not in the vacuum counts as matter. So stars count as matter, rocks are matter. But we're really going to just talk about stars, right? The physical matter of stars. We're probably not going to get into electromagnetic effects on space-time. We'll do a charge black hole. So okay, yeah. So like I said, so this is basically how matter controls space-time. Okay. One path we could get to. So if you could execute that, if you could use the stress energy tensor to calculate the Einstein tensor, to calculate the metric of space-time, you've now on this time coordinate, right? We're going to take cases that are simple, right? We're not going to take our cases right off the bat. We're going to take simple cases. So we're going to get rid of the time dependence for the basic study of the astrophysics of simple stars. So anyway, the syllabus can go either way, right? We can take this track. I should erase this stuff because I'm not here to give an advanced story about how this all works. I'm just talking about the problems we're facing, choosing how to go through it all, right? So we could do either route. We could do this route, or we could do this route. I think as having thought about this, I think this route is the more common route. It's the route the Inferno users. prerequisites, right? We discussed the prerequisites. What is a tensor 321? What is a manifold 211? We discussed some of the books that I found very useful. There are many other good books out there, by the way, but these are the ones that I'll probably be using to help assemble the course. Yeah. And we talked about the units that we'll be using, and then we talked about the syllabus. Okay, so next time we will do a basic idea review of special relativity that's relevant for this class. So let's begin this whole process by starting to think about physics in a way that is conducive to understanding general relativity. And of course, when I say that, I mean this is how it worked for me, and worked to the extent that I am familiar with this. I mean, I'm not certainly any more knowledgeable about this than many. This is just the way I like to think about things in order to align with the nature of the subject very well. And I think this is a great way of doing it. And it has to do with thinking in terms of world lines. I think world lines is really, there's a lot of information to extract just by really getting a sense of how world lines work. For example, world lines are followed by test particles, right? And there's a lot of interesting information about what is a test particle. World lines exist in space-time, right? And that's an important jump to from the notion of space and time to the notion of space-time. A lot of that should have been done in special relativity. And ultimately, the world line is sort of the foundational concept, in my opinion, to get to what I find it to be the most interesting thing, well, in the elementary form of relative general relativity, which is geodesics. Geodesics. So let's see how much we can extract from the world line as sort of a concept to get us thinking in terms, mentally, in terms of general relativity, in terms of special relativity. And then the key issue is to get that time axis, to get that x0 axis right there in the forefront of your thinking. If you ever think of the motion of a particle and you don't think of it in terms of a time axis along with the space axis, you're hopelessly stuck in the detached Newtonian view, and you're never going to ever get a good conceptual grasp of general relativity. So this implies, for example, that when you think of the orbit of a planet around the sun, there's the sun, or a star, and you think of the orbit of a planet around it, if your picture is like this, then you're never going to get anywhere in the subject. The picture that you need to have for a planet orbiting the sun is a picture that looks like this. You put that orbit in a plane. You put the sun at a point in the plane. The sun is just... The sun has a path through space-time that is a straight line, because we are going to do this in the coordinate system where the sun is motionless. And this planet orbits the sun. Let me just do a solid line. The planet orbits the sun like this. And that is the way you need to view orbits around the sun. You can also do a flyby orbit. A flyby orbit would look something like just fly by through time. And time has to be part of the actual geometric picture. If you don't do that, none of this is ever going to make real good sense. If you do it, it's going to make sense pretty darn fast, actually. One of the things that helps with this whole picture is now is understanding that you have to be moving. In this picture, you must be moving. You can't stand still in a geometric picture of space-time, because standing still would be implying never leaving that spot. There's a spot right there. It's that location x0, x1, x2, and x3. And if you're at that spot, and you're never moving from that spot in space-time, that basically means x0 is frozen, right? Because it happens at an instant in time. And time never stops, right? The best you can do is apply all of that movement into the time-like direction, right? But you must be moving through time. And that's a really interesting point. Say everything's moving through time, and you're all standing still relative to each other. So you've got several guys there. There's no real relative motion, but everybody's moving through time. How fast are you moving through time? How quickly is this point or is this particle moving through space-time? I mean, the sun is just sitting there moving through time. You can imagine another sun, maybe this guy, that is moving through time. Well, they should both be moving through time at exactly the same rate. Now, if there's no relative motion, between these two stars, then special relativity tells us that, yes, their proper time is the same. You can synchronize it, and it will stay synchronized. So, what is that speed that two things who are not in relative motion move through time with? And understanding that we are measuring distance in terms of time in terms of meters, that speed is the speed of light. There's only one possible speed. What else could it be? It has to be the speed of light. That's the only universal constant available to us. And so, everything moves through time at the speed of light. And so that's kind of a fascinating way of looking at the universe, especially just listening to this lecture. You're sitting there listening to this lecture, you're moving through the speed of light at sea. And if you're just picturing yourself sitting still, you're not doing what I'm telling you to do. I'm telling you to picture everything moving through time at the speed of light. Things that are standing still relative to you, your book, maybe the mobile device you're watching this on, everything is moving at the speed of light through time. You should actually think of it that way. You should think of yourself as flying through time at the speed of light, and you're not standing still at all. The problem is that everything is traveling at the speed of light, not just you standing still, but this particle that's on this flyby trajectory of the sun, that thing is also moving along at the speed of light. It's moving along this line at the speed of light. And this planet that's moving around the sun, it's also moving at the speed of light. It's moving along its whole line at the speed of light. Every one of these particles, at every point on its trajectory through space-time, has a four velocity. We'll call that the four velocity. And it's exactly the same four velocity you learned about in special relativity. So there's a four velocity at every one of these locations. There's a four velocity for the sun that's standing still. There's a four velocity for this flyby orbit. Right? There's every point and every instant there's this four velocity. And if I call those four velocity, say I call that v, right? The four velocity at this point here, I called it v. We know from special relativity, we know how to write down v. V is dx0 d tau, dx1 d tau, dx2 d tau, dx3 d tau. Okay. Now, we know that d tau is the proper time, so the proper time is the time that's clicking off along on the clock attached to these test particles that are moving down these world lines. Now, I haven't specified quite yet that these world lines are free-falling, right? I haven't said that, or said it specifically, but it doesn't have to be. What I'm saying is irrelevant of whether these lines are free-falling or not. This could actually be a rocket ship that is accelerating toward the sun, not only because it's falling, but it's got its engines on, or it's pulling away from the sun and it turns on its engines. It doesn't have to be a free-falling object. This guy going around the sun, let's say it is. The sun itself, of course, is just free-falling in basically empty space. The reason these guys are test particles moving around the sun is because they don't influence the sun. They don't supply gravity. All the gravity might be supplied by the sun. Although, I shouldn't even be invoking gravity yet. I mean, we haven't discussed it. I'm implying that this particle is moving in an orbit around the sun. Whatever keeps it in that orbit, it doesn't matter. All I can tell you is that it's following this trajectory in space-time. And as such, this is its four velocity. And all of these guys have a little clock on them, right? This is a test particle. What is a test particle? Let's talk about our test particle for a second. Our test particle, for the purposes of this course, will be some kind of little contained object that has a clock, which I'll draw as a little cesium atom, right? Cesium clock. And an atom is an oscillator, right? So that's the oscillator for the clock. But a clock has to have an oscillator and a counter. So here's a little digital register that counts ticks of the clock. So that's the clock, right? And then what else does it have? So a test particle has a little clock on it. It's got a certain mass, right? A test particle has a certain mass, but that mass is very, 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 very small compared to everything else. It's so small that it doesn't cause any gravitational effect relative to the problem that you're studying. So that's its mass is very, very tiny. So you've got a mass, but it's small. You've got a clock on it. Oh, and its physical extent is so very tiny that it doesn't experience any internal stresses or strains due to gravitational tidal forces, which we'll talk about that a little bit. You can put that in your memory bank for now. Internally, it has no stresses or strains, measurable stresses or strains due to tidal forces. When we talk about tidal forces, I'll do that in a lot more rigorous detail. So that's what test particles. Also, test particles, generally speaking, should have the ability to just emit a burst of light, right? So they should have some kind of lamp attached to it, I guess, right? So there should be a lamp on every spot, so it can emit a little sphere of light. So it can emit a spherical light wavefront. In flat space, it would be a perfectly going in all directions. That's what a test particle is. Anyway, so these test particles have this four velocity, and that tau in the denominator, this tau is the proper time, which is measured by the clock on the test particle. So we've seen this before, and we can break it down, right? We just take these derivatives, so the lab frame time or the coordinate time with respect to the coordinate time times the coordinate time with respect to the proper time. I know that looks silly, but that's because of our units actually. Then the space time with respect to the coordinate time with respect to the proper time, and the space time coordinates in a similar fashion. And then for dx3 too, right? dx3, dx0, dx0, d tau. And this is all special relativity, right? This is all our basic course where this guy here we call gamma. That's the gamma factor. And of course in our units this is simply 1. In alternative units this would be ct, right? That would be ct here, so this would end up being c. This dx, this would be in alternative units this would be dct dt. So that's how you may have seen it in your special relativity course where so you end up with a factor of c, but in our case c is 1 and then we don't have to do that. One of the nice reasons of choosing the c equals 1 instead of units. So we end up with gamma v1 gamma v2 gamma coordinates are for velocity. I'll put a little vector up there. That's a 4 velocity for a Newtonian particle, right? You give me v1, v2, and v3, I give you a 4 velocity. So you go anywhere on this world line, specify v1, v2, and v3, and you end up with this 4 velocity. And the velocity that goes into the gamma, so remember, I guess it's review now, right? Is 1 over the square root of 1 minus v squared. In many textbooks, when you use this equals 1, you end up with this as a beta instead of a b, and beta is defined as b over c. So if your units are not c equals 1, then you just take the ratio of b to make it beta, and you end up with the square root of 1 minus beta squared. But our unit c is 1, so we don't have to bother with that process, right? I'm just saying this because different people come from special relativity with different formats, right? So we just go with this expression for gamma, and v is the square root of v1 squared plus v2 squared plus v3 squared, right? This is where x and some terms get confusing. So this is the definition of our 4 velocity, but let's work this out a little bit. What is the magnitude of the 4 velocity? The magnitude of the 4 velocity is the magnitude of v mu, like that, which is going to be beta, alpha, beta, v alpha, v beta, right? This is our special relativity Minkowski metric, which we're always going to use as minus 1, 1, 1, 1. And that's our choice. Our choice of the Minkowski metric is minus 1, 1, 1. That's the flat space-time metric of special relativity. And so when we do this calculation, we will get, see, negative gamma squared. It's all going to be a magnitude, right? So it's negative gamma squared plus gamma squared v1 squared plus gamma squared v2 squared plus gamma squared v3 squared, which is going to equal minus gamma squared, gamma squared 1 minus v1 squared plus v2, oops, I'm going up space, plus v2 squared plus v3 squared, and that's going to equal, gamma, there's a minus 1, that's a minus 1 right there, right? It's going to be gamma squared over, or gamma squared, and it's going to be basically v, the magnitude of the velocity, minus 1. And, well, what is gamma? So let me bring it up here. But gamma squared is 1 over 1 minus v squared, and then the numerator of this thing is v squared minus 1, v squared minus 1 is the numerator. So that whole thing equals negative 1, but we're taking the magnitude, right? So it equals 1, which of course is the speed of light, right? The speed of light is 1 in our units. The point is that the magnitude of an arbitrary velocity, of an arbitrary full velocity, is always c, right? Which is what I was saying. You just sitting still are traveling at the speed of light. If you're sitting still, you've got gamma 0, 0, 0 is your full velocity, but the magnitude of your spatial velocity is 0, so gamma equals 1, and the magnitude of this thing is going to be, it's going to be 1. So you're traveling at the speed of light all the time. And that's the thing you got to think about. Nothing is stationary in general relativity. Nothing sits still. It's impossible to be motionless. You can talk about being motionless relative to something, I suppose, but as far as any form of space-time measurement, meaning you have any kind of coordinate system, everything is moving in that coordinate system along a world line. Nothing is stationary. And furthermore, what's even more interesting is that no matter what, the speed of light. And so that's a pretty profound idea, that nothing is stationary in this business. And so that's an important way of starting to think about general relativity, because we're going to be building these world line constructions, and we're going to squeeze 3 space dimensions down into 2 so we can visualize it like this. That's not too hard because we'll have enough symmetry in our problems that's okay. There are problems that I'd love to get into involving curved black holes where you can't really do it. You can't really squeeze everything down into 2 dimensions. So then you have to kind of imagine, well, how do you picture something in 3 dimensions? Like, if we have a chunk of space, right? If we have a chunk of space, how do we imagine this chunk of space moving through this chunk of space in all 3 dimensions, some arbitrary movement in this chunk of space? How do we imagine that world line? Because we can't add a time dimension. I've seen people try different things. I've seen people try coloring, right? They'll start with blue, and then as it goes on and on, it'll turn. As time marches on, the line kind of changes color. All right. I've seen people try to do it where shrinking. Shrinking is what? You're imagining this cube. This is the cube at one time, right? And then you imagine at a later time, the cube is this little thing, and it's kind of shrinking. And that shrinkage is the time dimension, right? This actually looks like something that people call a tesseract. This 4-dimensional cube. It's sort of got that 4 dimension. This is really not worth the trouble. I don't think it's worth your trouble trying to imagine that 4th dimension. But there's a lot of times where something like that might be useful. But for now, we're okay, because we're going to be able to squeeze our 4 time dimensions into 2 space dimensions and then 1 time dimension. So we're not going to have too much trouble with that. All right, so this world line concept, that's one big important thing I want you to think about. So the next thing is sort of one of these fundamental postulates ideas is that we're going to be talking about, let's imagine we have this world line, right? I'll stick to my sort of orbiting, I'm not even sure that that's a really good orbit. I think an orbit is better understood like this, right? You have this sort of orbiting object in our space-time, right? There it is, that's its world line. There's coordinates on this space-time. Remember how we drew in the what is a tensor series? We drew coordinates like this, and I said, call that x0 and x1. And the very fact that you can do that, right? The very fact that this is possible. If I say this is symbolically representing space-time S, I can actually go into space-time and draw coordinates on space-time. And the fact that that's possible, right? That I can put 4 coordinates on space-time, that means that space-time is a manifold. And that is kind of an assumption of our mathematical structure of the theory. We're assuming that we can't lay down coordinates on space-time, and that space-time is actually manifold. And the 4 coordinates are x0, x1, x2, and x3. And this process can actually be done. Let me erase this guy for a second. The implication of this, of course, is since it's a manifold, we know that that what we really have is we really have some R4 out there, and if this region of space-time is some chart, U, remember we were getting the charts U alpha was their name, and this mapping from R4, which has this coordinate grid, that mapping is the inverse of the chart mapping, laying down these coordinates into space-time. So when I draw this thing, and I say, okay, here's our x0, and here's our x1, and here's our x2 axis, this thing here is meant to be this. It's meant to be space-time with coordinate lines laid down through this inverse mapping from some R4. That's what this is. This here is space-time, and these lines I've drawn here are supposed to be this thing I've been symbolically talking about in the manifold lectures. So this is actually like a realization, an instance of this. And so there's some other R4 out here. There's some other R4 out here that's mapping into this region with some kind of inverse mapping and laying down these coordinate lines. Those coordinate lines, the coordinate lines are like this. And then, so the x0 coordinate lines, the x1 coordinate lines, the x2 coordinate lines. And it's chopping up and dividing up and slicing up space-time. So space-time is a manifold. And therefore, if space-time is a manifold, we have kind of all of those tools that we were talking about before, right? If I'm now going to say, this is a path through space-time, well, it's a path. It's a curve. Well, what's a curve? A curve in a manifold, since space-time is a manifold. I'm not even going to draw the coordinates. I'll do this. I'll draw these little coordinates, right? x1, x2, x0. The time-like coordinate will always be 0. We'll discuss what distinguishes a time-like coordinate from a space-like coordinate a little later. But if this is a curve, and here's our space-time manifold, and here's a path in space-time, and there's a test particle that's following this path, presumably. In other words, this path is modeling the motion of a test particle in general relativity. Well, what does this mean from our manifold perspective? Well, I have some interval on R1 and a parameter beta, and I have a map from that parameter into space-time, and that map is going to be called x alpha. Alpha, the parameter there is beta. It's a function of beta. So for every value of beta, I can create a point in the manifold whose coordinate is x alpha. And as beta moves from 0 to 1, this test particle moves from x alpha of 0 ultimately to x alpha of 1. And every value of beta in here, this mapping will now plot the location for the coordinates of this test particle at all these different points. So this might be x alpha of 0.5, right? For example. And when I look at x alpha, of course, I'm thinking of x0, 0.5, x1, 0.5, x2, 0.5, and x3, 0.5. Right? And that is how we understand the path in space-time. It is parameterized as a curve on a manifold. And that tells us quite a lot, right? I mean, once we have a curve in space-time, we can now talk about tangent vectors on that curve, just as like we had in the previous lesson, lessons about tangent vectors. And we can also talk about the length of this curve, and we're going to do that. We're going to talk about the length of this curve in space-time. But the point I'm trying to get now is, before we go into those specifics, is that space-time is a manifold. And that's basically an assumption of the theory, right? The theory depends on the mathematics of being a manifold. And so now there's a little potential for confusion here, I think. And I'm not sure I've ever really resolved it myself. But understanding that if space-time is a manifold, right? Here's our manifold of space-time. Remember, manifold requires that, okay, this region has a chart to R4, and every region has a chart to R4 if we are dealing with a four-dimensional manifold. Now notice that says nothing about the metric, right? Being a manifold does not tell you anything about the metric. Sometimes you'll see people say that because space-time is a manifold, every little region of space-time locally must look like a Lorentzian flat space-time. And I don't think that's the right way to look at it. It is true that every local piece of space-time looks Lorentzian, and that's going to be the last point we make in this first lesson. But all this says that every region of our manifold has to have coordinates in 4 dimensions. Now, in addition to that, it turns out that there's another assumption of the theory that does get you this far. We'll talk about that. But just because it is a manifold doesn't mean anything about the metric. All it means is that you can lay down coordinates, and it's a differentiable manifold, right? In the sense that the transition functions are all differentiable functions, just like we learned about in the Lorentz manifold lecture. So the key assumption that we're dealing with, though, is that space-time is a 4-dimensional manifold. Now, on top of that, then there's the first principle that's actually really important, and we'll cover that as our last subject for today. And today it's called the Einstein equivalence principle, the EEP. And the EEP is usually, I think it's worth talking about because I don't like the way it's presented in books when I learned about it, because the presentation doesn't get you to sort of the mathematical modeling of it. But the typical presentation is this guy in an elevator. And I mean, it makes a lot of sense. I totally get it. That, you have a guy in an elevator, and he's basically, the elevator's in open space. It shouldn't be an elevator, just say a guy in a box, right? And he's just floating in open space. There's no gravity, there's no earth, there's nothing. He's